Okay, combustion. Do you have the problem that you could read it out? Otherwise, I can bring it up.
Write an equation for the combustion of 1 mole of benzene. Use data from Appendix D to determine delta G at 298. The products of combustion are CO2 gas, A is CO2 gas, H2O liquid, and B is CO2 gas, H2O gas. Describe how you might determine the difference between the values obtained in A and B without having either to write the combustion equation or to determine the delta G value of combustion.
All right. So I got a question about number 35 out of the homework, and this is the combustion of benzene. Benzene C6H6. Benzene's a liquid. We have to, in thermodynamics, we have to put in the states, because if benzene's a gas that changes the energy, is in order to convert it from a liquid to a gas, we have to add energy. So if it's in the gaseous state, it's at a higher energy state than in the liquid state. It's in the lower energy state. Oxygen is a gas here, and then we're going to form CO2. But we have a choice here. You know, if we combust this at room temperature, then the water that's formed will be a liquid. You know, if we combust this at elevated temperature, then then the water might not be a liquid, nor will the benzene be a liquid. In fact, at elevated temperature, benzene has a pretty low boiling point. It boils like 80 degrees C or so. And so if we're forming H2O gas, probably the benzene's a liquid a gas as well, but we can ignore that for right now. And so in order to do the thermo, we have to have a balanced chemical equation. So we need 6 carbons, and we need 6 hydrogen. And let's check the oxygens. 12 plus 3, 15 oxygens. So we'll need 15 halves O2. And so the question was, calculate delta G?
Yeah, I can do that.
Yeah.
But my question was the last part.
The last part, okay, if we form 3 waters versus 3 gaseous waters, okay, this would be 3 times the difference. In order to convert liquid to gas, we need the delta U or the delta H of vaporization. Since we're doing this under constant pressure conditions, we're going to use delta H. Delta H already incorporates the work in forming, because we're going from 3 times 18. We're going from less than 100 milliliters to about 75 liters. So there's a lot of work that's done, right? But delta H already covers that. And so it's going to be 3 times the delta H of vaporization for water. In order to vaporize the water, I have 3 moles worth, and I got to vaporize that. Well, the vaporization of water is a well-known number. A lot of people have this memorized. In fact, if you take biochemistry, the first chapter of a biochemistry book is water. What's special about water? There's so many special properties about water that allow life here on Earth. And I was just looking at the moons of Jupiter, just as an aside, and I saw one of them was kind of interesting because it looked like the picture looked like Earth, but it wasn't a water lake. It was a methane and ethane liquid on the surface of the planet. Well, methane and ethane sustain life. Well, no, it'd be quite a bit different, because water dissolves lots of minerals and other important elements. Methane and ethane, completely different polarities, so maybe other things can dissolve wax, or something like that. But anyway, getting back to this, I'd expect this to be about 3 times 4, 120 kilojoules difference in energy. And so if we formed the gaseous water, we'd actually get 120 kilojoules less heat than if we formed liquid water. Okay, so that would be it.
Because of the hydrogen bonds?
Yeah, the hydrogen bonds. It's not just the hydrogen bonds, but this incorporates also the work, because in order to vaporize it, not only you have to break the hydrogen bonds, right, but you also have to do work. and the system's going to lose energy during that work. And so that means, to break the hydrogen bonds, it probably costs less energy than this, and then you got to expand it to 25 liters. Well, 25 liters, each liter is about 100 joules, so it's 2,500 joules, or 2.5 kilojoules right there per mole. And so times 3 would be like 8 kilojoules worth, 7, and then other stuff. So it incorporates, it's not just breaking the hydrogen bonds, but breaking the hydrogen bonds is critical. Because in the gaseous phase, you don't expect those hydrogen bonds to exist, otherwise the water molecules would be stuck together. All right, are there any other questions on homework or whatever else? No. Okay, today we're doing the lab. For the lab, we need goggles. Everybody have goggles? Okay, if not, I have some loaner goggles. We need shoes. Sandals aren't allowed in lab, primarily because of the broken glass, also spills. But I don't have any extra shoes, so. And then what are we doing today? We're doing our synthesis today. And so let's take a look at the synthesis. The compound that we're after is this. K3 Cr C2O4 3.3 H2O. And it's not going to be aqueous. Water is an amazing liquid. This is why the first chapter of Biochem book is devoted to it, because it can dissolve so many things. So many things like this. When we look at this, is this soluble in water? Yeah, it's soluble in water. But we don't want an aqueous solution. We want the solid. And so we've got to think about that. We're after the solid. How are we going to do this? We're going to synthesize it from. We're not going to synthesize it from chromium. This is chromium. You know what the charge on that chromium is? In this complex here, plus, negative. Plus 3 is the correct charge. Yeah, that's plus 3. We need plus 3, but we're not starting with plus 3. In step 1, we're going to start with chromium, not in the 3 plus, but chromium in the, not in the 2 either. The chromium in the, yeah, I heard that. So, did you say plus 6? You're thinking dichromate. One of the things is this. So it's not exactly what we need. We need this here, but that's okay. Tell me some of the properties of dichromate. What do you think of dichromate? What stands out about dichromate? Or is it just your average? No, that's my average anion. Yeah, it's an oxidizer, but is it just your average oxidizer, or does it stand out? Like maybe it's an exceptionally weak oxidizer? Maybe. Yeah. In fact, you'd expect it to be an exceptionally strong oxidizer. When I look at dichromate, the property that stands out is this is a powerful oxidizer. It's a powerful oxidizer, and it's also toxic. So the toxicity, yeah, you want to stay away from this. You don't want to inhale the vapors. Hopefully they cleaned up all the mess from the morning over there. They're good to check the balances. So the potassium dichromate, the salt that we're using, is located in the hoods. It's like in hood number 6, I think, or 7, and another hood over there. That way, if a little bit of dust is generated, it's all right. We don't want, if there's some dust generated, we don't want that dust to come into contact with what? And so potassium dichromate is a powerful oxidizer. We don't want it to come into contact with reducers, and so we keep it away from reducers. Because if you take a powerful oxidizer like this and you mix it with a powerful reducer, then you're going to have a explosion. And so, well, you know, I did have an explosion, you know, in this lab. In fact, it was involving this experiment here. I had an explosion. I wasn't a student. A student had an accident. I had a student who was making up this lab in one of my other labs. The other lab, we were doing something called qualitative analysis, and we were using nitrate. In fact, we were using nitric acid. What stands out about nitric acid? Nitric acid is a powerful... Nitric acid, nitrate, the powerful... No, not reducer. You know, if you look at the chart, you know, this will be a side here. If you look at the chart, there's nitrate in there too. Is nitrate on the reducer side or the oxidizer side? Well, you might think it's on the reducer side because it's native, just like you might think this is on the reducer side. You might think it's a reducer because reducers are electron rich or electron poor. Reducers are electron rich. So you might go, wow, this is pretty electron rich, so it's got 2 extra electrons, maybe this is a pretty good reducer. But that's wrong. This is not a reducer. It's not a reducer because those extra electrons don't belong to chromium. Those extra electrons belong to oxygen. And oxygen is very happy as is. Now, let me tell you something. This experiment, we're going to write a scientific report. We're going to write a formal scientific report for this lab. We don't do that for every lab. It's too much work. It takes too much time. And so what does a formal scientific report involve? It involves, you know, describing, you know, what you did and describing the chemistry of what you did. And so the chemistry of what you did, so this is the type of stuff you talk about, you know, dichromate, you know, some of the properties of dichromate, you know, powerful oxidizer. Why is it a powerful oxidizer? Because you would be explaining or describing this stuff because the target audience would know nothing about dichromate. You know, they want to know something about it. And so you talk about, you know, that, you know, some people might mistake this for a reducer because of this negative charge, but it's not. It's a powerful oxidizer because of what? Yeah, chromium is at a +6, as you said. Oxygen is a -2. Oxygen -2 is happy as is. That's where the extra electrons went. They went to oxygen to keep it at -2. Well, anyway, nitrate here, this is a powerful oxidizer, not nearly as strong as dichromate. If you go back to Appendix D, you'd see that dichromate's on that first page, you know, even above gold 3. But nitrate's way down on the second page. And so it's not nearly as powerful. But this is still plenty powerful because this is what we had. Well, I had the explosion Chem 1B lab. It was nitrate. It was actually nitric acid. This is a powerful oxidizer because it was the nitrogen. Yeah, nitrogen's what? +5. Yeah, +5. And so what happened was this. We were using 15 molar nitric acid. This was a qualitative analysis. So we had 15 molar. We had a waste jug full of 15 molar nitric acid. In this particular lab, we use ethanol. Ethanol, let's look at the structure of ethanol. Ethanol is your organic alcohol. You look at ethanol, is it electron rich, electron poor, or just happy as is? What do you say? Yeah, it's a reducer. Now, is it a strong reducer or a weak reducer? It's a strong reducer because it's quite electron rich. Do you see it's electron rich? How can you tell that it's electron rich? Yeah, the oxidation state. So we look at the oxidation state. So tell me what is the oxidation state on this carbon here? That's correct. -3, right? This carbon, -2. Hydrogens, all the hydrogens. This oxygen, -2. This hydrogen, +1. And so it means a totally different thing. For example, a -2 on oxygen is totally different than a -2 on carbon. Oh, on this carbon it's -1? That's correct. -1 is right. So a -2 on oxygen is totally different than even a -1 on carbon. If I have a -1 on carbon versus -2 on oxygen, which one's more electron rich? The carbon. And this is why I asked you to memorize some reference points. You need to memorize some reference points. Like the reference point I asked you to memorize was for oxygen and hydrogen. I asked you to memorize water. You know, what are the oxidation states in water? -2 for the oxygen, +1 for the hydrogen. Is water electron rich? Is it a powerful reducer? Is it a powerful oxidizer? Is water electron poor? No, water is pretty unreactive. So there's nothing special. When I think about -2 on oxygen, nothing special. There, that's fine. That's good. Everything's good. Okay. Same thing with the hydrogen, the +1. But when I look at the carbons, those are different. These carbons are electron rich. I like you to do it on the structure because what did I say? If you do the oxidation states based on the formula, like this, you know, why? You know, this is not in the book. This is in the book. If we do H6C2O, it's easier, right? Which goes first, hydrogen, carbon, or oxygen? This is chapter 3. Yeah, we have to do it both ways. We don't want to have to draw Lewis structures for everything. This is one we want greater detail that we'll do it Lewis structures. But does anybody recall why? Why do it this way? This way takes more time than just doing it off the formula.
Is that like an average?
Yeah, that's exactly the reason. It's because we get the average here. You know, hydrogen goes first, oxygen goes second, carbon goes last. Carbon's going to be -2. Are either of these carbons -2? No, none of them are. You know, I said -3 or -1. And so I don't like this one as much because it gives the averages. I like this one because we can see where the reactivity is. This carbon's, the left carbon is much more electron rich than the right carbon, but both of them are electron rich. Anyway, this is it. It's kind of funny because do you recall what the flammability reading on dichromate is? The flammability rating or the flamm? Do you remember it? Was it 0, 1, 2, 3, or 4? 4 being the worst. It was a 0. I don't agree with that because of this. Just because it's a 0, does that mean we don't have to worry about fires or explosions? No. Like this is it. You know what the flammability rating on oxygen is? O2 in air? What do you guess the flammability rating on O2 in air is? 0. It is a 0. But just because oxygen is a 0, do we have to worry about fires or explosions? Yeah, we do. We do. They give the flammability rating to not the oxidizer. This is a powerful oxidizer. This is way more powerful than oxygen. You know, we could have explosions. We can have fires without oxygen ever being present. It could be just totally in the vacuum of space, and this would work. But over here, this is where the flammability rating goes. The flammability rating goes on the reducer. And how flammable is ethanol? Highly or moderately or not really flammable at all? Ethanol's highly flammable. So ethanol, we would probably give this a, what, 4? Maybe it's easy to burn, right? So we give this a 4. This gets a 0. If this has a 4, this is a 0, do we have to worry about a fire? Yes. We do. And so what happened is this. The person was making up this lab, they use ethanol. And so we're going to generate some ethanol waste. So I told them to put the ethanol waste in the synthesis waste jug, not in the qualitative analysis, what we were doing, waste jug, because in the qualitative analysis waste jug, I have lots of 15 molar nitric acid in there. 15 molar nitric acid is what we call concentrated nitric acid. And you know what happened? What happened was, you know, they're behind, so they're rushing to get through the experiment. And they were over at the waste station. There are 2 waste jugs. And they poured the ethanol into the wrong waste jug, and it exploded. It exploded. There was a huge, huge bang. The whole hood lit up with a flash. Fortunately, the jug stayed intact because, you know, it wasn't capped, so it just shot up like this. But they were reaching inside the hood because they weren't that tall, and so they're reaching up the funnel, and so their face was partially inside the hood, and first-degree burns all over their face. I thought they were going to get a glass full of, a face full of glass, broken glass, but got really lucky. And their hair was singed, so fortunately, you didn't read about it in the news. So we did have an explosion, so we got to be careful. Now that was nitric acid. This stuff is worse, you know? And so we don't want to mix this with a powerful reducer. But you know what we got to do is we have to convert this into chromium 3+. And in order to convert it from chromium 3+, we got to go from chromium 6+ to chromium 3+. To go from chromium 6 to chromium 3 requires a reducing agent. Now, what reducing agent should we use? Should we use ethanol? What do you think? Good idea or bad idea? If we use ethanol, it's a very bad idea. You're going to get an explosion, for sure. Or, you know, there are different grades of explosion, but you will get an explosion. So we aren't going to use ethanol. That'd be way too dangerous. Do we want to use a stronger reducing agent or a weaker reducing agent than ethanol? A weaker reducing agent. And what is the reducing agent we're using? Oxalic acid. We're going to use oxalic acid. Now, is oxalic acid, can you burn this stuff? Does it burn as easily as ethanol? No. So for example, it's easy to ignite ethanol, but it's a lot harder to ignite oxalic acid. Oxalic acid is carboxylic acid. If we look at the structure of oxalic acid, it looks like this. It has 2 of these groups. What's the functional group called in carboxylic acids? Hydroxyl is the alcohol group. Oh, carboxyl? Yeah. Yeah, we have 2 back-to-back carboxyl groups like this. And so this is oxalic acid. It's like mirror image of. It's kind of an interesting molecule. If you look at this one, this carbon, do you know what the hybridization is? sp2. This one's sp2. Maybe I should draw it like this. So if I have sp2, I'm going to draw it like that. If I have sp2 and sp2, what's the geometry around carbon here? Trigonal-planar. And so this is a flat molecule. It's flat, like this. Except for this part. Do you know what the bond angle here is? COH? This is not flat. Yeah, the bond angle is 109. Some people will say 180, but it's just because I didn't draw it accurately. You don't have to draw Lewis structures accurately. Here, this is closer to 109. But it doesn't matter. This is not a three-dimensional structure. Actually, it's going to be distorted. When we have 2 lone pairs there, those 2 lone pairs lead to greater repulsions. And so it's actually compressed. This is closer to water. Do you know what the HOH angle in water is? It's not 109. It's been distorted down to about $90. I think that's pretty good. Too extreme. Or maybe you went from 109 to 108.
It's like a 1.5 degree difference.
Well, that would be for like ammonia. Ammonia would be like that. Water is going to be a little bit more distorted than ammonia. You know, ammonia should have a 109, but its actual bond angle is 107. Close to 107. Water is closer to 105. 105 is the angle. It's actually like 104.5 something is the angle. This is close to 104.5, so 105 degrees. That's the type of distortion. Otherwise, the structure is like this. Let's take a look at the oxidation states. Here, if we do the oxidation states based on the formula, what goes first? Hydrogen, carbon, or oxygen? Hydrogen always goes first, then oxygen, and then carbon's what?
3
Plus 3. In this case, the average is the same because the oxidation state and the structure here, both of these carbons are plus 3. A carbon in the plus 3, well, the oxygens are minus 2, right? All of them. And the hydrogens are plus 1. When I look at oxalic acid, does that look electron poor or electron rich to you? It looks electron poor. And electron poor species are what we call oxidizers or reducers? Oxidizer. So to me, when I look at oxalic acid, I think oxidizer. This should be an oxidizer. It's not going to be a very powerful oxidizer, you know, but I'd expect it to be an oxidizer because this looks electron poor. However, it could go either way. The reason it can go either way is this. Of course, if it's an oxidizer, it's going to take electrons, but it can also be a reducer because carbon is not in its maximum. What is the maximum positive oxidation state for carbon? Plus 4. So, hey, there's one more electron. One more electron it can lose. And so if that loses electron, what would we form? And so we're going to completely oxidize it. Just take that. Yeah, it's just got one electron left. We're going to take it. It's the last remaining electron in the valence shell. We take it, what do we form? What are we going to form? Carbon tetraoxide? Carbon pentoxide? What do you form? Carbon trioxide? From carbon trioxide? We're going to completely oxidize it. What do you guess our product is? If we completely oxidize it, that is, take that one remaining electron, what do you think? What do you guess the product's going to be? That's right. We should get carbon dioxide, because in carbon dioxide we've hit carbon at plus 4, so that last remaining electron is now gone. So I expect this to be a much better oxidizer than a reducer. So as far as being a reducer goes, this is going to be very weak. A very weak reducer. So if we say that ethanol is highly flammable and we give it a 4, if we give ethanol a 4 on the flammability rating, what would you give oxalic acid? Do you expect oxalic acid to be highly flammable like ethanol? What other carboxylic acids do you have experience with? Maybe vinegar. Have you ever tried to catch vinegar on fire? Does it ignite like alcohol or acetone? It's a lot harder to ignite, right? And so if you gave ethanol a 4, what do you think you'd give oxalic acid? Flammability rating. A 1? Yeah, that sounds reasonable, like a 1. And so a 1 means it's not a very good reducer. Not a very good reducer. And so, of course, we wanted this. Otherwise, if we use something stronger than this, we might risk explosion. And so this is an example of skeleton redox, chapter 5. In skeleton redox, we know what we want for the oxidizer. We want the oxidizer, dichromate, to go to chromium 3+. And we want the reducer, oxalic acid, to go to CO2. So we're going to completely combust this stuff. Are we combusting this in oxygen? Are we? Oh, well, actually, there's not going to be a flame in this case. Hopefully there's no flame. Are we going to oxidize the oxalic acid? Oh, I know what we do here. We just H2C2O4 plus O2 yields CO2 and water. But the case is no. We don't need any oxygen here. In fact, we have something more powerful than oxygen. What is it? This. We got dichromate. We don't need any oxygen. And so what we're going to do is we're going to do chapter 5, skeleton redox. Chapter 5, skeleton redox. Although, you know what? This one occurs on our chart. So I could just copy the half reaction off our chart and skip all the skeleton redox stuff. But I'm not going to bring up the chart. It takes too much time. So I got 2 chromiums here. And it's so fast to balance this 1 chromium. So we have to go to 2 chromium 3s. And then I got 7 oxygens here, 0 oxygens here, so I add 7 waters here. And then I have 14 hydrogens on the right, and I have 0 hydrogens on the left, so I just go 14H plus here. And then let's look at the charge. -2 plus 14 gives us plus 12. Plus 3 times 2 is plus 6, plus 0 is just plus 6. And so I've got to balance this by adding negatives. So I need to add 6 negative electrons. They'll drop plus 12 to plus 6, and then they balance. And so I just add up everything on the left. So I got dichromate plus 14H plus 6 electrons. This goes to 2 chromium 3 plus 7 H2O liquids. And so this I could have just looked up on the chart. That half reaction is on the chart. However, this half reaction is not on the chart. This half reaction we have to solve using chapter 5 method. And so to use chapter 5, it's not like combustion. We don't have any oxygen. We don't have to have any oxygen in this reaction. And so we got to balance this by the same method, 2 carbons, 1 carbon. And so this needs to go to 2 CO2s. And then I got 2 hydrogens here. I have no hydrogens here, and so I'll just do plus 2H pluses, and then let's take a look at the charge. 0, 0, plus 2. And so I need 2 electrons over here, and then that's it. And so this half reactions, H2C2O4 goes to 2 CO2s plus 2H plus 2 electrons. So the remaining 2 electrons are gone, 1 electron in each carbon here, as we expected. Now, we'll combine the 2 half reactions. Let's see, this gains 6 electrons here. This produces 2 electrons. And so what I'm going to do is I'm going to multiply this second half reaction times 3. And then add those half reactions together. So we'll get dichromate plus 14H plus 6 electrons plus 3 oxalic acids goes to 2 chromium 3 pluses plus 7 H2Os plus 6 CO2s plus 6H plus 6 electrons. All right, let's simplify. The 6 electrons cancel, which they have to. Then I have 6 H pluses here. I can cancel those out. That leaves me with 8. And then that's about it. And so I'm going to have dichromate plus 8H plus 3 oxalic acids yields 2 chromium 3 plus 7 H2O plus 6 CO2. Then we check to make sure everything's still balanced. It's still balanced, both atom and charge. Looks balanced. This looks good. Now, there is a driving force for this. Well, let's take a look at the driving force for this. This is our oxidizer, we said. And so the conjugate reducer is this. This is our reducer. So the conjugate oxidizer is this. And so we'll just label these. This is our oxidizer. This is our reducer. On the product side, this would be our reducer, and this would be our oxidizer. Now let's compare the oxidizing agents. What do you think is a stronger oxidizer? Dichromate and acid, or carbon dioxide in water? Do we need the chart? Wait a minute, that's not on the chart. I didn't see carbon dioxide on the chart. Therefore, I can't answer this. This is not a fair question. Or is it? This is a totally fair question because, I mean, this is just common sense. You know, just think about the damage. If you had a cup full of dichromate in acid versus some carbonated water, which one would cause more damage to your tissue? It should be obvious, right? And so it's obvious. This is going to be much stronger. This is going to be much weaker. And so that means oxalic acid must be a stronger reducing agent than chromium 3 plus. And so we have driving force here. Now, even though we're using a very weak reducing agent, this is still a potentially dangerous reaction. In the past, what's happened is, what do you want to do? You know, we have a choice. We could add the dichromate to the acid, or we could add the acid to the dichromate. Does it matter? Dichromate to acid or acid to dichromate? Does it matter? It does matter. This is another safety rule in chemistry. Have you ever heard AA? Add acids? That's a safety rule in chemistry. We always add the acid to the water. Why? Yeah, because of superheating and boiling or whatever else. The way I like to think about this is like this. You know, maybe this is not a good analogy because I said this morning and it didn't click with anybody, I think. But if you think about a pool filled with piranhas, right? A pool filled with piranhas would be like your dichromate. And then you have your oxalic acid. Oxalic acid would be like the victim, the food or whatever. And so what you can do is if you throw the food into the pool filled with piranhas, is it going to be kind of a violent reaction or is it going to be kind of a mild reaction? It should be mild or violent. Actually, you know, it's going to be violent. I don't know if you've seen those videos where some animal walks unintentionally across a stream filled with piranhas. Have you seen that? And water churns and things start to get more fun. Versus, let's say you have one piranha and you threw that one piranha into a pool filled with whatever piranhas eat. Then is that going to be really violent? No, it should be mild, you know, just one piranha. But if you had a pool filled with piranhas, it would be a different story. So this is why we add acid. We add acid, which is vigorous, violent,
We add the acid to the water. The water is mild, mellow, right? And so the same thing here. This is the way we control it. You know, you throw in one piranha in there. It's okay. Things aren't out of control. 2 piranhas. So you have control over that rather than letting all the piranhas attack, right? This is the same thing in acid and base. You know, you don't want water being a weak base in that case. Well, it's the same thing here. You know, this is very violent. And so what we do is we control the addition of this to this. And so we have a pool filled with oxalic acid. Oxalic acid, is it very reactive? Is it very violent? No. And then we slowly feed in, you know, the predator in there, right? And so that's what we're doing here. Already what's happened today is somebody dumped it in all at once. They dumped it in all at once. Fortunately, it didn't splatter all over, but it's happened in the past. One person, I don't know if you can still see one of the hot plates. One person dumped in all the dichromate at once. It started foaming and splashing. They got it on their hands, arms, all over the hot plate. Just this mess. It was a nasty mess. And so even though this reaction looks kind of mild because oxalic is such a weak reducer, it's still potentially violent. And so be careful of this. Well, anyway, once we get this reaction done, then we're there. So at chromium-3. So in step 2, what we want to do is we want to attack the chromium-3 plus. And so it's already reacted. We formed our chromium-3. We're going to attack it with this, potassium oxalate. You know, potassium oxalate sometimes is mixed up with potassium dichromate. They kind of look similar, the formula. It's already been mixed up today. That people thought this was the dichromate. But potassium oxalate, C2, chromate, Cr2. Going with this, this is soluble, it's a strong electrolyte, and what we're looking at is we're looking at the oxalate ions. The oxalate ions would look like this. Just take off the hydrogen off oxalic acid, we're going to get oxalate. Each of these oxygens will have 3 lone pairs here on the ends here, and a negative formal charge. And so what do you see here? Well, I see positive, I see negative. What's going to happen? There's going to be a reaction there. Maybe it's a metathesis reaction, or maybe it's a Lewis acid-base reaction. And in this case, it's going to be a Lewis acid-base reaction that occurs between these two. And so here, the oxygen is going to be what we call the electron pair donor. The electron pair donor is known as the Lewis base, right? Lewis base. Lewis bases in this type of reaction are also given another name. You know, this is my Lewis acid, that's my Lewis base, the Lewis acid-base reaction. Lewis bases are also called ligands. This is a special kind of ligand because this ligand, if I look at it, has 4 oxygens. All 4 of those oxygens want to attack this chromium-3, but it turns out only 2, and it turns out only these 2 can. So these 2 oxygens will attack it. And so I'll have one attack here, and then the second will attack it here. And so when this happens, I'll have the chromium. Now, with these complexes, we just retain the charge, and then we'll throw in the oxalate here. Now that lone pair is used as a covalent bond, a coordinate covalent bond. So we got these 2 bonds going here. Like this. Now what do I have? Well, I got potassium oxalate, and I have oxalic acid, because what do you want as a limiting reagent? Do we want dichromate as a limiting reagent or oxalic acid? Do you want to have leftover dichromate, or do you want to have leftover oxalic acid? You want leftover oxalic acid. You don't want any leftover dichromate. And so we're going to have leftover oxalic acid. So we're going to have both oxalate and oxalic acid present. Well, you know, oxalic acid can do the same thing. So for example, if we had oxalic acid here, what can happen is this lone pair here can attack the chromium like this. But if it attacks the chromium, it throws a positive formal charge on the oxygen. To get rid of that positive formal charge, what happens is these electrons get pulled into the oxygen, kicking the hydrogen off as a proton. And so that can happen twice here. Like this. And that'll kick that hydrogen off as a proton. Now, the situation is, why not these oxygens here? Why not these oxygens here because of the structure? You know, if this is trigonal planar, then these oxygens on the opposite side of this is going to be flat pancake-like ligand. And this is a special ligand because normal ligands only bond in one place. This ligand bonds in two places. A normal ligand is called a monodentate ligand. Dentate meaning a bite or biting into the central metal. And so this ligand is called a bidentate ligand because it can bite into the metal with two bonds, each oxalate or oxalic acid. When oxalic acid comes in there, this is what will happen to the hydrogens. So what we'll do is we'll put this one back up here. Now I'm going to try to draw this more three-dimensionally around chromium, but not around the oxalates. So I'm going to use the dash and the wedge diagram here. And then I'll throw in another oxalic acid here. Or oxalic, it was oxalic acid, now it's oxalate. What happened to the acid part? What happened to the acid part is it gets kicked off, and so we'll end up with two H pluses out here somewhere in solution. And so those H pluses got knocked off. Well, it turns out there's still room. There's room for one more. And so if we get one more, let's, rather than going with oxalic acid, let's just go with an oxalate. If you get one more oxalate come in here, then so this base comes there and attacks our acid. You know, the chromium is still 3+, the way we think about it. And the oxalates is still 2-, if you think about it. But have an attack here and attack here. And what we end up with is called an octahedral complex. The structure is octahedral. And to complete this octahedral, we only need 3 oxalates, not 6 oxalates, because oxalate is a bidentate ligand. So 3 oxalates will bond 6 places. So here's 2. Four of the 6 bonds, 2 ligands, and the last one here. Do you think there's room for a 4th oxalate? You think we could fit a 4th oxalate in there? No, there's no more room left. We stop here. So we stop here. What do we call this ion? Try. Well, let me write out the formula. The formula is going to look like this.
the chromium in the center, and then we'll have 3 oxalates attached to that. The total charge here is chromium's 3 plus, oxalates are 2 minus. So minus 2 minus 4 minus 6 plus 3 gives us minus 3, or 3 minus. And so the name of this is the rather than calling it oxalate, we change the ending. We call it oxalato. Trioxalato chromium or chromate. It's not a cation, it's an anion. Chromate. Trioxalato chromate, Roman numeral 3. The Roman numeral 3 comes from the positive 3 charge, not the negative 3 charge. And so this is a trioxalato chromate 3 ion. This is what we're going to form in solution. This is aqueous here. And so what kind of reaction is this? This is a acid-base reaction, Lewis acid-base reaction. And so we formed our complex there. Now the final step is we need to do a metathesis reaction. What were metathesis reactions? Do they involve? Favorable ion combinations. Now, basically this, what we want to do is we want to precipitate out the salt, the potassium salt of this anion. And so right now, that's the problem, because right now in solution, we still have potassium ions. The potassium ions will be the counter ion. We've got lots of potassium ions. So those potassium ions will help neutralize the charge on this. This is AQ. What does an aqueous solution of this consist of? An aqueous solution of this consists of potassium ions. These potassium ions are going every which way. Just random. These potassium ions can go whatever. And then we have these ions and those ions. And the ions are pretty much independent of one another. They don't have to interact. That's what happens. This is soluble. And so those ions can go wherever they want. Well, one way I can make these ions come together is to force them together. I can force these ions together by evaporating all the water. It's like the fishes. Fish in a pond, the fishes are going to kind of stay separate and they're going to go their own way. But if you start evaporating the water, more and more, the fishes are going to get closer and closer. And the same thing here. We can evaporate the water and force the ions closer and closer. And pretty soon, once all the water is evaporated, the ions are going to have to come together and we're going to form salt. But there's a big problem here. We can't do this. We can't do this because, if you think about this, like sea salt. Sea salt's a mixture of salts. But when you evaporate the water, seawater, to get sea salts, are you getting pure salts or a mixture of salts? You're getting a mixture of salts. The thing is, we have lots of other junk, plus other junk. What other junk is there? Well, excess potassium oxalate, excess oxalic acid, whatever else. Right? Ions. So if we evaporate all the water, then what's going to happen? What's going to happen is we're going to get a mixture of salts and solids that come out of solution. We don't want that. What we want to do is we want only the potassium and the complex to come out. And so what we need to do is we need to accomplish a metathesis reaction. But there's a problem. And that is if I take my 3 potassium ions, which are aqueous, and try to force those to precipitate out with this, am I going to be successful? No, because these are like fish in water. They're just going to stay apart. You can try to coerce them together, but they aren't going to come together and precipitate. They're going to stay apart.
And so how can we force these ions to come together, to react? Only these ions, not all the other junk. Well, what we have to do is we have to take advantage of solubility. I was thinking about this, I was thinking about the moon, the moon on was it Jupiter or Saturn? I guess Saturn. Was the moon on Saturn? And they're saying it has oceans of ethane and methane. The oceans of ethane and methane, are going to dissolve different things. At one time, maybe on the Earth there was, but now Earth is, methane and ethane is what we call a reducing environment. We've got powerful reducers there. Now we live in an oxidizing environment, which is oxygen. So methane and ethane aren't stable. But anyway, let's go back to this. So how can we force these to come together, to react in a metathesis way? Well, let me tell you how we're going to do that. How we're going to do that is this. These are plenty happy in water. But if you get a nonpolar, like say this were liquid methane or ethane, would this be happy like fishes? No, if this were methane and ethane, then the potassiums and the complex would come together. It would be like fishes in an ocean of methane and ethane. They're looking for oxygen to breathe. So they're going to come together like that. And so this is the same kind of thing here. What we're going to do here is this. Unfortunately, we can't convert this from water to methane or ethane liquid, but we can do this. Water is super polar, but ethanol is also highly polar, but is it as polar as water? No, because ethanol has that, I erased it, I wasn't supposed to erase it. Ethanol has a CH3CH2. That's like ethane and methane. If you look at methane, methane's like this, CH4. CH4, this is actually -4. Methane's very rich in electrons. Methane's a great reducer. And so if we look at this, ethane's kind of a mix, right? It's got that polar end, the hydroxyl group like water, but it also has this hydrocarbon end like methane and ethane. And so it's kind of a mix. It's not totally polar. But the great thing about ethanol is it's miscible in water. What does miscible mean? It means it's infinitely soluble in water. And so what we could do is we could do this. We could start off with these ions in water. So this is the water. And then what we're going to do is we're going to add ethanol. And ethanol just mixes easily with water. In fact, it's infinitely soluble in water. And so what we can do is we can just add some ethanol to this. And what we can do is we can add so much ethanol to this that this is what's going to happen. If we continue to add more and more ethanol, it's going to force these ions together because this is not very soluble in ethanol. And so what we do is we add so much ethanol that the liquid looks like ethanol because there's just not much water in there. We aren't going to get rid of the water. The water's still there. It's just now that the liquid resembles ethanol rather than water. And that's going to force these together. Now the water actually is going to get trapped because if I look at the structure of this is a solid like this. If I look at the structure, this is a typical salt lattice. And so in that solid structure, I'd expect to see my potassium ions like this, followed by the chromium complex here. -3, the potassium ions here. This would be one formula unit. A formula unit would just be one unit of this. It's not a molecule, it doesn't form molecules, but it'd be 3 potassium ions and 1 of these. And these would just alternate, into a solid
lattice. Okay, when we form a solid lattice like this, there are usually gaps or void spaces between the ions. Do you remember some of the gaps or void spaces, the names for those? Two primary ones. There are two, especially in a face-centered cubic lattice. If you have a face-centered cubic lattice, the two gaps between ions that you should know the names of are what? Don't remember? All right, in a face-centered cubic lattice, the two holes or gaps or voids are called the octahedral hole and the tetrahedral hole. And inside those, you can fit molecules, you can fit ions, you can fit other stuff. And so what happens is this. What happens is, there's water present. There's water present in air, there's water present in this. And sometimes the water's attracted to these ions because water's polar too. But it's not going to be as strongly attracted because water is partially charged rather than fully charged. So there's going to be an ion dipole style attraction. And so what happens is water gets stuck sometimes in these void spaces. And what results is this. For every formula unit of K3 complex, I can fit 3 waters into that void space. So I'll have 3 waters with this, another 3 waters with this as the crystal grows. And so what I form is not what we call the anhydrous solid, that is, there's no water stuck in the voids there. We form the .3H2O. And these 3 H2Os aren't liquid, those are water molecules that are trapped in the crystal lattice. And so this is what we're after. This final step is metathesis here. We're getting favorable ion combinations. Unfortunately, those favorable ion combinations don't happen in water, but they'll happen in ethanol. If we add too much ethanol, then we're making it too much hydrocarbon. Like we might start getting some of the other stuff coming out. And so there's kind of a balance here. What we're after is, we aren't after maximizing yield. We're into maximizing purity. We want high purity stuff. If we lose some, it's okay. Just as long as what we have left is very pure. And so that's our goal. In synthesis, there's another thing here. So you might be used to trying to scrape off every last crystal or every last drop or every last whatever, but in synthesis, sometimes we don't worry. Another thing we don't worry too much about in synthesis is precision. Like, for example, if we overshoot, let's say it calls for 3.6 grams, I get 3.89 grams, no big deal. Just as long as you keep the limiting reagent and the excess reagent the same. So if you overshoot on one, you better undershoot or overshoot the other just to balance things out. So if you overshoot on the limiting reagent, then you better overshoot on the excess reagent, otherwise you have the risk of swapping the limiting and excess reagent. All right, are there any questions on this?
So on the lab report, you want all this stuff you just explained on it?
Right. On the lab report, you're going to write all this stuff up and explain to the reader all the chemistry that's happening, the chemical reactions, the properties of these things, So the reader might go, why the heck are you adding ethanol? What's the purpose of adding ethanol? And normally what happens in Chem 1A, Chem 1B is people cookbook things. People go into autopilot and they just do it. They don't know what they're mixing. They just know they got to mix 50 of this and 100 of that, and they don't really care what they are, right? This is what happened to that student. The student's in autopilot mode. They aren't really thinking what they're mixing together, right? They're just doing it. I can easily tell when students are on autopilot mode because, they don't mix things the same way as somebody who understands what's going on. So to somebody who understands what's going on, the ethanol addition is done differently than to a cookbook. Somebody who's doing cookbook, the procedure says add 10 milliliters of ethanol. So they add 10 milliliters of ethanol. Sometimes that's not enough. The person who understands what's going on is thinking, okay, the purpose of ethanol is to precipitate this. So if that's the case, then I'm going to keep adding ethanol until I've maximized the precipitation and then stop, right? And so some people, they might have had too much water, not enough, too much of this, too much of that, and so there are lots of little variations that happen, and you can make on-the-fly adjustments if you know what you're doing. And so this is a critical step here. And so what's happened what's happened is somebody's added, they added the right amount of ethanol, 10 milliliters. They got a tiny amount, barely any product, almost nothing. And that's because they were cookbooking it. They weren't looking at what they're trying to accomplish. In this step, we're trying to maximize this. So keep adding the ethanol until you stop seeing. We don't want to waste it. Obviously, you don't want to keep adding gallons and gallons of ethanol. But then again, we don't want to cut ourselves too short. We do this for everything. So for example, later on, when we do a precipitation, we keep precipitating until it's stopped. Not until the instructions say to stop. Does that make sense? And so this is so you want to think about this. So this is why, you know, when you write the report, you're trying to explain, you know, it's not just mixing this and this. This is what's happening. This is what you're trying to accomplish in these steps.
Kind of explain again why cost take long. You said it was, I think you said it's less polar. It's less
polar, exactly. It's less polar. So these things are this is very simple, but amazing. Amazing story. So, like, if you're on that moon in Jupiter, you know, that's very nonpolar. Methane and ethane are what we call nonpolar. So what would dissolve, and I was thinking, what would dissolve on methane and ethane oceans on this moon in Jupiter? What would dissolve with things like wax? Wax would dissolve, you know, and other, like, greasy type substances, right? And so what we're doing here is we're making this. These are very polar. Ions are extremely polar. They got full charge. And so we're making the solution, the liquid, or the solvent, less and less polar. So the more nonpolar we make it, the less soluble it becomes. Not only that, we're going to do something else, another trick. Another trick in this is to lower the temperature. Right? We want to lower the temperature because what happens when you lower the temperature? Does solubility go up or does solubility go down when you lower the temperature? It goes down. So that's also going to aid in precipitation of our solid. When we do this, there are some other things we try to take care of because, like I said, we want purity over quantity. When we do crystallization like this, there are two ways that crystallization normally happens. One way is you end up with lots and lots of tiny crystals. You end up with lots and lots of tiny crystals. Okay, that's fine. You get lots of tiny crystals. Or you end up with a few big crystals. What is preferred? A few big crystals or lots and lots of tiny crystals? A few big crystals. The reason is, for a crystal to grow big, there can't be too many impurities and there can't be too many defects in that crystal. And so the more impurities you have, the more impurities you introduce, it's going to stump or inhibit the crystal growth. And so if you get a good big crystal, then you know, in a crystal, you know, the ions have to be in the proper positions. Not like 0 Kelvin proper, but still they have to be in the proper positions to propagate the crystal over large volumes. And so what we try to do is this. And when we're looking at crystal growth, there are two processes. There's nucleation. Nucleation is creating a baby crystal. And there's growth. The baby crystal grows. And so when we do crystal growth, we shoot for minimum nucleation. We don't want to nucleate too many baby crystals. If we don't nucleate too many baby crystals, then those little baby crystals will grow into big crystals. Versus if we nucleate tons of baby crystals, we have high nucleation, then we aren't going to get big crystals. We're going to get small crystals. And so we're after big crystals here. Now, why it does that is because of the solvent here. Which brings me to this interesting story. You know, things like this. You know, there's a lot of aluminum on Earth. You know, there's like these Caribbean islands consist of 100% aluminum oxide. Problem is, it's as aluminum oxide, Aluminum oxide, is this stuff very soluble? No. And it's really hard to dissolve. And so if you want to dissolve aluminum oxide, what would you try? You try lots of different things, but in terms of polarity, you know, it doesn't dissolve in water, so you might try to dissolve it in something more polar than water or less polar than water. Well, aluminum oxide consists of aluminum 3 plus and O2 minus. Do you want more polar or less polar? More polar. If you can find a more polar solvent than water, you might be able to dissolve aluminum oxide. Just like, you know, this stuff precipitates out of ethanol. So we have a solid here. What we need to dissolve this is a more polar solvent. So just the opposite. If we wanted to reverse this and dissolve this, we would use a more polar solvent than ethanol. What's a more polar solvent than ethanol? Water. Well, water's not enough to dissolve this, so we need a more polar solvent than water. What's a more polar solvent than water? No, benzene's nonpolar. And so we'd look for something like that. Okay, I'll stop here and then